Hi everyone, this is the setup video for the RC circuits lab. So in part one, we're going to set up an RC circuit, which means that we have a circuit with a resistor and a capacitor. So if you look at figure one in your instructions, you'll see how I hook up one of the 10,000 ohm resistors that we've been using a lot in series with one of the 56 microfarad capacitors. So if you look here, you can find it. It's in the bag with the MPN that starts with, you can see in the instructions in step one, RK1E560M. Okay, and you'll also notice when you look at it, it'll also say 56 microfarad somewhere on it. Okay, like here on this one. Okay, and you'll also notice that like the LED we've used before, it has a short leg and a long leg. And so the long leg corresponds to the positive and the short leg to the negative. So, so it's going to be important so that when we hook up the circuit to power, right? So with the ILab device, I have one cord in the 3.3 volt port, one in the ground. And so I'm going to connect the 3.3 volt port to this one end of the resistor, okay? And then when I go to place the capacitor in series with it, I want to make sure that the longer end, okay, is facing toward the resistor, okay, because the resistor is connected to the positive end of the 3.3 volt port. Remember, it's considered positive. Okay, and then I'll connect the ground to the short leg, the negative leg of the capacitor. Okay, so your circuit should do something like that. So we have essentially a series circuit. Okay, and then what we're going to do is we're going to, for this first part, we want to try to charge up the capacitor and then discharge it through your LED. So again, we have the long leg for positive, the short for negative. So in that row where we have the positive end of the capacitor plugged in with the same row as this end of the resistor, that same row we want to plug in the long lead of the long leg of the LED. Okay. All right, and then we'll just leave the other end. Just leave the other end up in the air like that. Okay, so not actually connected to the breadboard. Then we'll take another jumper cable here, and we're going to connect it to the negative lead of the capacitor. Okay, and then the other end with the pin is just going to be free. Okay, so what we'll do is once you open up your ILab software, once you turn the device on and you see that it says connected on your software, that means it's on, and that power from the 3.3 volt port is now going through the resistor and the capacitor. And it only takes a couple seconds for it to fully charge up. Okay? So then what you'll do is you'll disconnect your the wire that's connected to the 3.3 volt port. All right, you'll take the wire that has the free pin, and you're going to touch it to the LED on the pin that's sticking up in the air, and you should see it light up. Okay, so I'll try that again. I'll clip the 3.3 volt port back onto the resistor. Give it a couple seconds to charge. I'll disconnect it. Then I'll try to touch it to the leg of the LED again. Okay, and what I noticed here is a very easy mistake to make, is I didn't actually have the LED in the same row as the resistor and the capacitor. That was one row off. So that's why I was having an issue there. So very easy to have little mistakes like that happen and get a little frustrated, but don't let it get you too frustrated. Okay, there's always some troubleshooting with electronics. That's just part of the nature of it. So we'll try here one more time. I will flip on the 3.3 volts port to the resistor. Right, it should be fully charged now. I'll disconnect it, and then I'll touch the free end of the wire. That's connected to the negative end of the capacitor. And I'll touch the wire. And oh, so you saw it kind of blink there really quick. All right. So you could also do it if with the 3.3 volt port connected to the resistor, and then it'll constantly be charging. So every time you discharge it, you can tap on it again. You can tap on the LED again, and you can see it light up. I'll get dark here so you can see it. So, all right, so once you got it lit up, then you know that you have everything connected right. So you can see in figure 2 there, I have a close-up of how it should be connected already, okay? Then in part 2, we're gonna find a true capacitance of the capacitor. So it's labeled as 56 microfarads, but you recall from the previous lab that the 10,000 ohm resistor was labeled as 10,000 ohms, but it has a certain tolerance because of how it's manufactured. So it's never going to be exactly the same. So we're going to try to find out what the true capacitance is. And part of that will be by using the true resistance that we measured for the 10,000 ohm resistor in the previous lab. Okay, so we'll go ahead and take out the LED. We don't need that anymore. And then we'll essentially keep everything else hooked up here the same, okay? We're still gonna have, the only thing we're gonna take out from that circuit in figure 2 is the LED. We're gonna use everything else, and then we're just gonna add one more wire. So I'm gonna take one wire and I'm gonna plug that into the A7 port. Okay, so remember your analog 7. Okay, and then we're going to connect that to the middle of our circuit here, to the end of the resistor that's not touching the 3.3 volt port. Okay, and you can see that in figure 3 of the instructions. Okay, so by having it hooked up like this, we can, if the device is on, which I can see mine timed out, so I'm gonna have to turn it back on again. And as soon as you turn it back on and it says connected, it's the power is flowing through the resistor and the capacitor, and that capacitor is gradually getting charged. And so what we'll do is, once it's charged, all right, you just wait a couple of seconds, and you're going to take, this time you have to take off the pin, the alligator clip that's connecting the resistor to the 3.3 volt port. And then you're going to want to touch that with the free pin you have, touch that to the end of the resistor that was connected to the 3.3 volt port. And you want to touch it and hold it there, okay? And as you're doing that, that's when you're going to want to turn on your software. So I'm going to switch my screen here and show you what that's going to look like when you're discharging the capacitor. So I'm going to let's see, we're using analog 7. Okay. And what I'll try doing here is I'll try to switch from my camera looking at to the camera looking at that, so you can watch me actually touching on the resistor as I discharge it. So first, we're going to connect the 3.3 volt port to one end of the resistor. Just leave it for a couple seconds. It's fully charged now, so I'll take off the 3.3 volt wire. I'll click record, and we should see it's about 3.3 volts. All right, which we would expect because we were plugged into the 3.3 volts sensor. And then we're going to watch as I touch the free end of the wire that's connected to the negative end of the capacitor. I'm going to touch that to the end of the resistor that was connected to the 3.3 volt port. And as I touch and hold it there, we see it go through that decay. All right. So I waited about 27 seconds before I actually touched the wire to the resistor. So if I want, I can zoom in a little bit. Maybe I'll do the side-to-side zooming. And then we see there I got a nice exponential decay. Okay, so that whole first almost 26 and a half seconds, you can see that it was at 3.3 volts. Okay, but then once we started discharging the capacitor, the voltage started going down. Started going down exponentially. So, okay, and so now what you want to do here is you want to extrapolate some data from this. So, so keep this graph here. You're going to come back to it in a little bit and collect some data from it using the data tool. But for now, you're going to click on the toolbar symbol right on the bottom left of the graph and go over to where it says export to CSV. And you'll see here in the upper right, this green box come up saying that the data has been saved to my documents folder. So you see when I go to my documents folder, there's a file called IOLab work files. And this file was installed when you installed the software onto your computer. So it has all kinds of things in here. This is where it saves your calibration data, all your other data that you collected from all your experiments. And then here's the export folder. So then you can see that there's a CSV file in there. I'm going to open that with Microsoft Excel. Okay, so the purpose of putting this in Excel, looking at this spreadsheet, is just so we can manipulate some data here. So you can use this with any spreadsheet you want. I'm going to do it with Excel because that's what I'm most familiar with. That's what you have access to as a UMass student. You have free access to that, to download all of Microsoft Office for free, even if you're not a regular UMass student and you're just taking this class one time, you still qualify as a student, so you can get that for free. So if you don't have it and you're using some free word processing software, you might as well download this while you can for free. And so I'll show you how to do it through here. But essentially, we have we only need two of these columns. We need the D column and the F column. Okay, because the D column tells us time. The F column tells us the voltage. So I'm going to go ahead and delete A, B, and C. And then that one in between them now. So now I just have the time and the voltage. Okay, and I'm going to go down. What I'm going to do is I'm going to, because for the first 26 seconds, it was just at 3.3 volts. I'm going to go scroll down to 26 seconds. Okay, so so about 20. I'll do a little after so I can see here.
It's sort of bouncing around 3.24, 25, 26. But then clearly I see here, it finally goes, boom, down to 3.238. So I'm going to delete everything before 26.41 seconds, okay? Just because that's all when, before I started discharging the capacitor. So the only data we want is the data before or the data after we started discharging. And the point of this is we're going to try to do a curve fitting using some graphing software. So what also will help is if we scroll down to and delete everything after about 0.1 seconds. Okay, not 1 second, but 0.1. So over here. So about here. So I'll delete everything else after that 0.1 seconds. All right, still decaying, but it's as far as trying to fit this to an exponential function, it's gonna look a lot better. We delete everything after that. So now we have data. Now we have time and we have voltage. So what we'll do now is we'll go over to the instructions. Okay, so we're in part 2 of the instructions under, let's see, so step 5 has the link to Microsoft Office where you can go get that for free from the IT website. And then now we're in step 8. So we're going to click on this Plotly chart studio. Okay, and we see here we can have a spreadsheet up here. And what we can do is we can copy over our data. Okay, so we'll take our time and our voltage and put it over there. Okay, and then we'll go over here to where it says plus trace. We're going to add a trace. All right, and we'll add a scatter plot trace. And for the x-axis, we want our time. Okay, and then for the y-axis, we want our voltage. So then we have voltage versus time. So essentially, we have the same thing, the same picture we had in the iLab software on that graph. Okay, only now the iLab software doesn't allow us to do anything, do any curve fitting, but this software does. So on the left side here, you'll see the Analyze tab, and under that is curve fitting. So we'll click on curve fitting. We'll click up here plus fit to add a fit. We'll select the trace. There's only one of them, trace 0. And under the family function, we'll click on the drop-down menu and click exponential. Okay, and then we'll have to run the fit. Okay, and we'll see that it'll give us some numbers here. So these 3 parameters, A, B, and C. Okay, and this is all the function of, you can see above where it says function family, it's in the form of A plus B times E to the CX power. So the A parameter actually corresponds to your offset voltage. So that's one of the things you're going to want to record in your lab report. And I want you to think about it. You've taken the offset voltage measurement several times now, so this should be pretty similar. Okay, the B measurement is not going to be useful for us for anything right now, so we can ignore that. But then we do want to have the C parameter because that's going to tell us, if you look at your instructions in step 9, we see, right, here's the function, right? and so when we actually model the voltage drop across the resistor when the capacitor is discharging through it, we can find it by this equation where we say the final velocity, or the velocity after a given amount of time, is VI, the initial velocity, which would be 3.3 volts, times e to the minus t for time over tau. Okay, so so the C parameter, which you'll see here in 10, is actually equal to 1 over RC, okay, or 1 over tau, which tau is the resistance times the capacitance. So so you'll use that C here. So for me, it's 1.7, and you'll see it's negative, and then you'll see in the equation, it's actually e to the minus t over tau, so those negatives will cancel out. So you don't really have to worry about the negative. So for me, I would just use 1.7. Okay, and from that, now that we know that the tau is, for me, is 1.7. No. Yeah, here, I'll round to 1.7. So for me, it'll be 1.7 equals 1 over RC. And the R is the resistance of the 10,000 ohm capacitor, which we calculated in the previous lab. So you want to get that record of what the true resistance was, and then you solve for C, and you get the true capacitance. Okay, so that's one way we can do it. Another way that you'll see here in steps 11 and 12, we'll get another, we'll actually plot this linearly. So we'll see here that the natural log of the voltage versus time, if you follow my steps here, will give you a linear fit. And so what we'll do is we'll go back to the Excel software, and for my voltage, what I can do in order to do that in Excel is really easy. You just, I'll find this free box here in column C, and I'll type in equal sign ln, and you'll see the function ln, natural log, will show up. So I'll click that green box. Then I'll click my first voltage data point and click enter. Okay, so that gives me the natural log for the first data point. Now you don't have to do that for every single one. In Excel, there's a nice feature where if you click on the box and you want it to apply that function the same way, everything down the column, what you do is you put the cursor, which is, for me, is a white plus sign there. If I bring it all the way to the bottom right of that cell, you see it turns black. And then if I double click, it applies that natural log to everything. Okay, so now I have all the natural logs of all the voltages. So I will copy that, and then I'll go ahead and put that in my Plotly software. Okay. Then what I'm going to want to do is I'm going to go back and add a new trace. So on the left side here, I'll click on traces. I'll click the add trace button. Again, we'll do a scatter. Our x-axis will be time again. So for me, that's my A column. And now I want my y to be the C column, the natural log. Okay, so now I've plotted, and you see, for me, it's a green line, the natural log of the voltage versus time. Nice linear line. Okay, then we'll go over to curve fitting, and then we'll add a fit. All right, we'll pick our trace. Now it's trace 2. I don't know why it skips trace 1, but it does. The automatic family function is already set to linear. So all we have to do now is click run. Okay, and so if you look and follow my steps here, my derivation, you'll see that the natural log with respect to time is equal to 1 over tau. Okay, so the natural log over time is the slope. So our slope, right, we have mx plus b for our form, which we're familiar with from 6th grade math. And m is our slope, and we'll see here it's, for me, it's 1.63, okay? So it's pretty similar to what I had before for my exponential curve. I have 1.7. So it's pretty close parameter there. So now my slope is 1.63, and I can, again, solve for similarly to before, where tau is 1 over the resistance times the capacitance, and we'll solve for C again. So this way you get 2 different ways of measuring the true capacitance of the capacitor. Okay, then the final part, in part 3, you're going to want to calculate the initial charge. Okay, so the initial charge is the initial voltage, right, which should be about 3.3. I think for me it was like 3.25 something. So it's the initial voltage times the true capacitance. So you can average the 2 you got in the previous part, and then and use that capacitance. So that will give you the initial charge. The second way we'll get the initial charge is, I did a little derivation here, and you notice it as an integral, so a little calculus, but you don't actually have to do the calculus, because that's one thing the iLab software can do, is it will run the calculus for you. So you see here the initial charge is 1 over R, 1 over the resistance, that true resistance of the 10,000 ohm resistor, times the integral of V dt. Okay, so that integral of V dt is, in the iLab software, is the area under the curve. Okay, right, because voltage is on our y-axis, times on the x. So the integral, or the sum of all those voltages, is that area under the curve. Okay, and the area, if you click and highlight with the data tool on that whole area under the curve, right, you don't want to do anything underneath where it would before it started discharging. You only want while it was discharging. Okay, and then up here in your numbers, you get some, right, you get an average, but you also get this one here, data point called A, is the area under the curve. For me, I got 1.996 volt seconds. Okay, so that's my integral of V dt, is 1.996. Okay, and so and what we derived here, the initial charge is that integral, my 1.996, times 1 over R. Okay, and you should get something pretty similar, right? You should get a charge, initial charge, pretty similar to what you got in step 1 of this part. Okay, so that's going to be it then for the RC Circuits lab.